My name is Brett Brewster, and today I am going to be going over a two-dimensional projectile motion simulation application that I created. It is built with HTML, CSS, and JavaScript. So here is our HTML file. Here is our CSS file. And here is our JavaScript file. So I'm going to go over very quickly what each of these initial conditions will do, and then we will run a few simulations and see how accurate our simulator is. So this first initial condition is our height. That is going to be our starting position along the y-axis. Then we have our displacement, that's our starting position along the x-axis. Our angle is with respect to the x-axis, so 45 degrees is going to be something like this. We have our velocity, that's our initial velocity. A gravitational constant, so we have Earth or the moon. We have a drag medium, so right now it's going through a vacuum, but we could change that so that there's air resistance introduced. Then we have our projectile shape, so we can do a streamlined body, a sphere, or a cube. A surface area for that shape, and the mass of the projectile. Now, all three of these are only going to be relevant if our drag medium isn't a vacuum, and because we're going to be using a vacuum the first couple simulations we run, we won't be adjusting these at all until then. And then finally, our color box here. This is going to change what color the simulation looks like, so what color the trajectory comes out as. And that's nice because by changing our color in between simulations, we can very clearly see each one, because when we have a few of them on here, it's easy to forget which one was which. So without further ado, we will demonstrate the functionality. So here is our first simulation, and before I pull up the actual numbers on this, what we're expecting theoretically with these initial values are a maximum height of 22.94 meters and a maximum distance of 91.76 meters. And we have it logging out a height of 23 meters and a distance of 91.96. So that's very close, just about 0.25% error, which is acceptable, but we will adjust our DT, and by decreasing the step size, we're going to decrease our error, but it's also going to take significantly longer to run. So now we will run the simulation, and we're going to expect that our numbers will be much closer to our theoretical 22.94 and 91.76 meters respectively. And we have 22.95 and 91.81. So yes, both of those numbers, the maximum height is now off by 1 centimeter and the maximum distance is now off by 5 centimeters. So for the sake of time, we are going to change our DT so that everything runs much quicker and reset this here. But that was just to show that the accuracy goes up as our step size goes down. So here we'll run our initial simulation again at 45 degrees. And now we're going to change the color to a green. And we're going to change our angle to 60 degrees. And what we're going to expect when I hit simulate is it should go higher. The maximum height should be greater, but the displacement should be less than it was in our 45 degree trial. So let's see what we get. So our maximum height was definitely higher, and our displacement was lower. So that's exactly as we expect. And now we're also going to run it at 30 degrees, and theoretically, these should end up at the same endpoint. So we'll make this yellow. And here we are. Yes, hitting it almost exactly at the same displacement. And again, if we decrease the step size, those would get even more accurate. Now let's change the gravitational constant to the moons. We will change our angle back to 45, and we will change our color to gray to indicate the moon. And what we're going to expect is this is going to follow along this initial turquoise colored line right off the start, but because the force of gravity is so much weaker, it is not going to have this same curvature. It's almost going to look linear. It's almost going to look like just a straight line at 45 degrees here. And that is what we get. You can definitely see that there is a little bit of curvature, but it's minimal in comparison to our first simulation. So now this is actually still running, even though it is off of our canvas. So once this finishes running, we will get a maximum height and a distance. And because the force of gravity on the moon is about 1/6 of what it is on Earth, we're going to expect that our height will be about 6 times greater and our distance will be about 6 times greater than it was in our first. And 23 times 6 is 138, so that's spot on. And then 92, 555, pretty close. All right, so now we'll go back to Earth and we will start introducing some air resistance. So here we have a drag medium of air. We're actually going to do a streamlined body for our first example here, and we will change it to a nice pink color. So what we're going to expect is at first it's going to follow along this turquoise line, and as it starts to slow down due to the new drag force, it is going to be a little bit shorter. The maximum height's not going to be quite as high, and the displacement will not be as great as it was in the original 45 degree in the vacuum. So here we go. And that's exactly what we were expecting. It's a little bit shorter in terms of the y and the x-axis. Now let's change our projectile shape to a sphere. So this is not going to cut through the air quite as well. So it's going to be even shorter in terms of the max height, and it's going to be even shorter in terms of the maximum displacement. And we'll change this to round. All right, so now we see the sphere was quite significantly shorter than the streamlined body. And now we're going to do a cube, which is the least aerodynamic of these three shapes. So we're going to expect this to be it's going to run into the most air resistance, which means it's going to have the shortest height and the shortest maximum displacement out of all of these trials. And it's exactly what we expected to see. So now let's increase our mass significantly here. And because we're increasing our mass, but we have the same surface area, the same projectile shape, and the same drag medium, we aren't going to be increasing our drag force. So we have the same drag force, but a much higher mass, so our acceleration due to drag is going to be significantly lower, and that's going to mean that this is going to go much higher and much further. It's going to more closely resemble our original turquoise line than this white line did in the previous one. So we'll use orange for this. So here we can go. We see it's not quite as good in terms of height and distance as our streamlined body, but let's see if we can make it even better. So by decreasing our surface area, we are effectively going to dramatically decrease the drag force, and we still have a very high mass, so we have a smaller drag force, and it's still being divided by a pretty big mass, relatively speaking. So this, my prediction is going to go higher and further than the streamlined body did, even though it is a very unaerodynamic shape. Here we go. And yeah, it's almost exactly the same with how small the surface area is. It is almost exactly the same as our initial vacuum conditions. So that's it in terms of demonstrating the functionality. There are a few modifications that I would like to make to this application. The first, and probably the most obvious, is to introduce a z-axis to make this a 3D projectile motion simulator. Another thing that would be really cool would be to add set projectiles. So for example, I'm going to reset this here. In our starting conditions for surface area and mass, these are representative of a basketball. So it'd be cool if you could just very quickly switch between a basketball simulation, a football simulation, a sniper rifle bullet, and a shotgun, a BB from a shotgun shell. Something like that, where you have a bunch of different projectiles that you can very quickly switch, and that will change your surface area and your mass. And then another cool thing that could relatively easily be added would be a find furthest angle. So what that would do is it would determine which angle is going to give you the greatest distance, and it would only show that trajectory. And when you have a height of 0, your furthest distance is always going to be 45 degrees. But when your height is greater, by decreasing the angle, you can actually get a further distance. So let's show that off here real quick. So here is our first case. Just went slightly off the screen there, but that's okay. I think we'll still be able to prove our point. So now let's change this to 42. Change this to white. And if the lines cross, which they were about to, so we'll run this again at a velocity of 20 so that everything stays on the screen. So here's our 45-degree angle example, and then we will do a 40-degree angle example. And as we can see, the 40-degree angle actually goes a little bit further than the 45-degree angle. So it'd be cool to just have something that goes through and it loops from 0 to 90 and picks out which angle actually gives us the greatest displacement. So I hope you enjoyed this quick demonstration of this application. I would love to hear your thoughts, your questions, and your suggestions about this app. And until next time, take it easy.